Okay, so hello everyone. My name is Mateusz Pusz, and I am a C++ trainer and a chief software engineer at EPAM Systems, where I am mostly dealing with projects from finance domain with high performance and low latency constraints. Today I would like to share with you an alternative approach to polymorphism that might provide better results for you if you are also dealing with such constraints as I am doing. But first, let's talk why we are talking about this today. What is latency? Latency is time needed from stimuli to the response of some system or some operation. It's measured in units, like hours, minutes, seconds, units again, by the way, today, at least for me. Low latency. This is the way how we achieve and beat our competition. If you are faster than the competition, then the finance domain gets more money. The project gets more money because people come to us to trade and get money for them. When I'm asked by the other engineers how to develop fast code, I mostly say how not to develop fast code. It's much easier and much more important to limit your set of tools you're using rather than know something more. In low latency, we care mostly about the worst case execution time, which means that when you have different results from experiments, we mostly are interested in the slowest one, not the average or the fastest ones. So what are the things to avoid on the fast path? You shouldn't use tools that trade performance for usability, like shared pointer, stud function, and similar stuff. You shouldn't throw exceptions on likely path. Exceptions are really, really fast as long as they are not used on the fast path. So you shouldn't throw there. Dynamic polymorphism is really slow. Multiple inheritance, RTTI, dynamic memory allocations. And today we'll be talking mostly about those two, dynamic polymorphism and dynamic memory allocations. This is the thing that we will be trying to limit with our solution. So how to do it? This is typical usage of dynamic polymorphism. You have a base class that is non-copyable, has a virtual destructor, and some virtual function that's pure virtual in the base class. And you have some child classes that override this specific function with the same signature. In most cases, when dealing with polymorphisms, you have to dynamically allocate memory for child classes, and you're working mostly with base class pointers with this way. Probably all of you know it. With alternative approach, with variant, what happened? Okay. You have two possibly unrelated classes with equal or equivalent interface. You have a variant of those two, and you say visit for some lambda function that is templated lambda function for every type v full. So you're accessing either this or this depending on what variant stores. So that way we are achieving polymorphism. This is a polymorphism, but not dynamic one. The code is shorter, faster. It produces you value semantics, works on any unrelated classes, so you don't have to create some fixed hierarchy of classes. You can have types that are just similar to each other. And because of this, there's more flexibility in the design. So basically, that's all. I'm done. This is the feature that I wanted to show you. I was faster than 22 minutes. But as we have some more time, I have some bonus slides. So let's look how it works in some examples. This example for today will be a finite state machine. A finite state machine is an abstract machine that can be in either of the finite number of states it has at any given point of time. So this is the finite state machine we'll be implementing today. It has states like idle, connecting, connected. It has events that trigger transitions between states. And you can see that some events have some predicates in order to be fired. Finite state machine is defined as a list of states, initial state, marked with this dot here, and conditions for each transition. So let's analyze the first case, the traditional dynamic dispatch. We have some finite state machine with function dispatch of an event. Event will be, in this case, a numerator. And we'll have state, pointer to state in finite state machine. This pointer, the state will be a base class that will have on event pure virtual function that takes this event. And we'll have like 3 child classes for each of the states. So the state will be again non-copyable. It will have a virtual destructor. It will have on event that takes our event type. In this case, it will be a numerator, but that's a generic design, so it can work with any event types. For finite state machine, again, this is the event type for the finite state machine. We store state pointer in the machine. We have the constructor that initializes the initial state. And we are having this single dispatch done here, calling on event function of the state base class. If the result is not null pointer, then we assign a new state. Yeah, so it was single dispatch, and this is dynamic one, yes? So we are having here the virtual functions. This means that the dispatch is being done in runtime. Every time you see virtual, it means slow, it means runtime, it means overhead, in case you care for performance. If you want to implement the transitions, you have this finite state machine here. I will use this alias that, of course, will not be used in production, but for sake of slides, I define such an alias for state of events. And I'm having the state IDO that inherits from this state. Connected. The state connecting has some additional members because it has to handle this logic of those predicates. And all of them have on event virtual method member function. And yeah, these are those three member functions, and they are implemented in a typical way. So you are checking if the event is connected, then something is happening. Otherwise, nothing changes. The same for second one and for third one. Please see that we have a lot of dynamic allocations connected with such finite state machine, which means slow again for our use case. If you'd like to test the transition or just use them, you can use fall expressions. So you have a dispatch for finite state machines and a list of events. And using comma expression here, you can just verify if after those events you will end up in a state that you expected. OK, so single dynamic dispatch. It's open to new alternatives. You can always add new states, for example, to it. It's closed for new operations. If you have only like on event or dispatch function, you cannot add easily second one without modifying the base class and all other child classes in the system. It's multi-level because you can theoretically inherit classes as much as you can, as many times as you can. It's object-oriented. It's based on objects. And that's all about the first case. The second case is double dynamic dispatch. So let's assume, for example, that one of our events wants to provide some data to our system. Like, for example, event connect would provide an address to connect with. So this is not just a simple enumeration. It wants to provide some data to your machine. And in such a case, you would have to build another polymorphic tree. You would have to provide event-based class that will be non-copyable. You have to provide child classes for each event. And here you have the state idle on event. You can implement this, of course, this way. If base class event is dynamic cast of event connect, then do something, otherwise do something. But that's, of course, a really bad idea. So I will use so-called double dispatch, which is also known as visitor pattern. We produce another function dispatch in event-based class. It gets state. Our finite state machine will take dispatch state to do first dispatch. So we are first dispatching through events. Each event will have dispatch member function implemented. And what will it do? It will pass it to state on event, a virtual member function with current type of the event that was dispatched in the first step. So right now we are not working with events base class, we are working with specific event types from the first dispatch. So as you probably already realize, our state has to have different interface, it has to have overloads for every single event in their implementation. So, for example, for state IDO to be implemented, you will have on event implementation where you will just create information. You have state idle and event connect. It means that you should go and go to the state connecting state and provide the address from the event to the state. So this is how class diagram looks for this use case. It's pretty complicated design already, as you can see. We have base class for state, we have base class for event, we have states, we have events. Everything is fixed by the implementation details. So you cannot design this differently that it's here, because this is how polymorphics work. You don't have flexibility in design. You have just to do it, because otherwise it's not possible to implement it. One thing that bothers me always with double dispatch and similar classes with polymorphism is that I often tend to rewrite the same stuff for every single child class. Especially when you have hierarchies like having 100 or 1,000 classes, child classes, then I'm having to write this 100 or 1,000 times. As you can see, it's pretty repetitive, and we can replace it with so-called curiously occurring template pattern, CRTP, that the pattern is working that way that it takes child class as a template parameter type, and then it's casting current at this pointer to a child class, and can run this function once only in one implementation. So with this, our implementation looks this way, that event connect is inheriting from event CRTP, and event connect is provided as a type to this class. And in fact, I'm right now able to provide all of the classes on one slide, which was impossible on the previous cases. So in order to implement this, I have once again the same finite state machine. I have those on event for every state, and I already have the dispatch being done. I don't have to check, like in the first case with ifs, what is the event, because I already know this. I'm in state idle, and event connected comes. So I just do the transitions for every case. And again, a lot of dynamic memory allocations, which means slow in our case. So to test transitions, again, we can use default expressions, and we provide dynamic allocated events to our system, because we have polymorphism again. So again, we deal with performance issue while using Finite State Machine. Double dynamic dispatch is similar to the previous one, with the difference that it's not open to new alternatives, because you cannot easily add things like states, for example, because you've seen that our events, because our state had overloads for each single event in the system. So if you would like to add a new event, you would have to refactor the base class for state and add a new member function. So right now it's close to new alternatives, it's close to new operations, it's multi-level, it's object-oriented. So talking about variant, because this is the subject we want to introduce today, I will show you only two design choices because we have limited time today. But architect of such an approach has a solution, has a possibility to use a solution that works for him. There is more than one way to do it. You are not constrained by the implementation details. So in this case, we'll have separate unrelated events that do not have any member functions, and they may store some state, like this one. Event connect, this is the same what was in the double dispatch case. And we are creating a variant of those events. States are similar. They are independent. If they need to store some state inside, they store it. And we have a variant of states. Transitions may be a visitor class that has call operator for every possible operation here. So if you have state idle and event connected comes, then you go to connecting. And you're doing this for every single case. And what's missing? The default case, yes? What to do in other situations. So we are adding greedy template here that takes every other state and event combination and just return null opt for our cases. Note that we are using not only variant, but also optional from C++17 here. Implementation of such engine can be implemented this way, that you will have state variant as a template parameter, and you store the variant here, not a pointer to a base class. And you provide here optional state variant as a return. type, and you provide state for visitor dispatching. And also assign a new state if this is not null-opt. Event variant is the variant of events. It can be used this way, or I will show you alternative approach in a next solution. And you also dispatch it here in the visitor. And of course, transitions are here. So this is our visitor. Design looks like this one, that we have Finite State Machine that has loosely connected states, aggregated in a variant, loosely connected events, aggregated in a variant, and transitions. That is a visitor for the logic of our Finite State Machine. So all the logic is external to the machine, state, and events. While testing the transitions, once again, you can use the fold expressions, and you are just passing specific events by value here. No dynamic allocation needed, but still events provide some additional values here. And the last case for today will be a variant that stores a transition logic in Finite State Machine itself. For this, we'll have a Finite State Machine that has a dispatch, has a new state, visitor, state event. This is similar to the previous case. The difference is that right now we have here derived type. And this derived type means that we have CRTP again. So we are saying that our child type of our Finite State Machine, so thing that derived from our Finite State Machine, is this. And then we can forward with our lambda visitor that takes everything, every state and every event, can forward it to our child class for implementation of on-event function. You can also implement this in this way, that you lose the variant of events that was here. You just provide a template function. So basically, you end up with the overloads of dispatch for every event you have in the system. If you are fine with such overload set, then the logic here for visitor is easier because you are dispatching over only one variant than two. And you don't have to put all of the events in one variant, so it also loses your design constraints in this case. So we have connection FSM that inherits from our FSM and provides this CRTP type to the base class. And we have states. And we have on event provided in our Finite State Machine. So not in a visitor like it was previously, but they were, as you remember, it was forwarded here from this generic visitor directly to our on event in a child class. So all our implementation of the Finite State Machine child class provides the logic for all the transitions, the same way like it was before. So once again, the diagram. This time we don't have events of a variant of events. They are unrelated classes. And you can see that you have a lot of possibilities here for design by yourself. OK, but this talk is about performance, about working with low latency or high performance software, yes? So what are the results? First of all, I don't believe too much in the micro benchmarking stuff, because that stuff is mostly working on hot hashes. It's some synthetic test. You have to measure in your production code how it behaves. I can just tell you that I will, of course, provide you the results from micro benchmarks, but I will just tell you that in production code, we've seen those changes visible on the high scope of the performance of all the project, not only some specific small algorithm part. So it really matters. For the case of the micro benchmarks, I provided bigger Finite State Machine in order to make CPU branch predictors and CPU caches work harder. And this is what I got. For single dispatch, I had this one. Please note that this is a percentile scale, so it is not linear scale. It's not also logarithmic, it's just the percentiles I selected. Double dispatch, of course, is worse. And this is what I get for variant. This is why it's worth to go for value semantics, to not use dynamic memory allocations, to not use dynamic dispatch. As a summary, inheritance variant. Inheritance, if you remember, was open only in the first case. In the second, it was close to new alternative. Variant is always close to new alternative, but when dealing with finite state machine, we have finite set of states. We will not be willing to extend those. It's close to new operations, and in fact, variant is open to new operations because, as you've seen, either states or events or finite state machine do not have too much logic there. They are like simple classes. All of this is provided externally, and you can always add new operations on those. Of course, you cannot inherit easily from variants, so it's single level, but we don't care in this case. Object-oriented functional approach, pointer semantics, value semantics. Design is forced by the implementation details, so you cannot design this in a different way. Here you can have many different choices of design. Dynamic allocations, no dynamic allocations, strict interfaces, duck typing, which is fine. And in my opinion, it's complex, simple, slower, and of course, faster. And that's all, thank you. I think that we don't have much time for questions. It was perfect on time, thank you. I'm here on the break, so you can ask me.